So let's start with data structures. So data structure is like a very integral tool to coding. There you will find in ICPC and everywhere problems which are directly based on data structures, and in other cases there will be few problems in which you will be needing data structures. Maybe there is some algorithm, and ultimately when you will be coding, you will be needing data structures to code them efficiently. So as I hope you are all familiar with the basic data structures like stacks, queues, dequeues, linked list, circular linked list, heaps. So let's quickly start with a problem. So there is a problem called seed trick, card trick at Spoch. The URL is www.spoch.pl/problem/seed trick in capitals. Okay, so I'll explain the problem. The problem is that there is a magician and he has a pack of cards in his hand. So what he does is he takes one card from the top, puts it at the bottom, then opens the top card, and that appears to be 1. After that, he removes the first card, this one which appeared, and he takes 2 cards, does this operation twice. That is, take 2 cards from the top and put it at the bottom. And again he just unfolds the top card, and this time it appears to be 2. He removes this 2 again, and now he takes 3 cards and put them at the bottom, and now the number appears as 3. So he does it n times, and each time at the ith step the number which appears is I. So the magician is just following a trick, and the problem is that he has already done a permutation of these cards. He's already just shuffled the deck in such a way that he is able to do this trick. So you have to figure out that in what order he should arrange the cards so that this trick works. So for this problem, there's one straightforward way, that's simulation of this, that you follow what is being said, that just take the top card, maintain a queue, take the first card, just enqueue it at the back, and as the problem says, just follow a queue structure in that. Another approach could be that you can view this problem as a circular queue or a circular linked list. So you maintain a doubly linked list, you travel that many steps. At the ith step you travel I turns, and for the first step you travel 1 and 2, delete this node, then go travel 1, 2, and then delete the third node, and this way you can just solve this problem. However, the complexity for this problem will be like n square, because at the ith step you will be going I steps in a linked list, travel I steps, and then delete the node, and again I plus 1 step and then delete the node. So we will this is one problem. At the end of the lecture I'll be teaching interval trees through which we can solve this problem in a more efficient way.
One more thing, when you see limits, you can also judge what could be the possible time complexity for the problem. So a normal system that will be using in ICPC or world finals, the system can perform 10^6 basic operations in 0.01 seconds. So it's like 10^8 operations in 1 second. So using that calculation, you can actually judge how many operations you can perform in the given time limit, and what could be the actual time complexity. So like in this case, if n was 20,000, so n square means you will have to perform about 4 into 10^8 operations, which will take 4 seconds. This would exceed time limit which is allocated for the problem. So you have to do something which is better than n square. So just seeing the time limits, you can actually judge what could be the approximate time complexity of the problem. So that is one way, meaning first step towards approaching a problem.
Yeah, like he said, mostly in most cases, whatever problem you will see on Spoch, etc., the order required is like worst case 10^8 or 10^9 computation which we can do, because the time limit is like 1 to 10 seconds. So in this way, if the limits are specified like more than 20,000 or something, then n square won't work. So let's go to another problem. So okay, so there is another problem which I am suggesting, that's expedition. Expedi is the code at Spoj.
A would be less than B and A would be less than C. This is the relation that we follow. So you can see that if this relation is followed in this whole tree, the root is bound to be minimum, because root is minimum, then root is smaller than both these nodes, and a similar relation follows for all its children. So you can see very simply that if you need to get the minimum in this heap, you can directly see the value at this node. Is this clear? Okay. Now let's say we have a heap which is made up of a few elements. We need to see how do we do an insert in this heap and how do we delete an element from this heap. One very important thing to take care of while making a heap is that you have to take care that the heap is always balanced. So even while inserting, we have to take care that while inserting, if we move from n nodes to n plus 1 nodes, the tree should look similar to a complete binary tree having n plus 1 nodes. So what we do is, the heap normally has two operations: percolate up and percolate down. So what we do is that, suppose the tree looks like something like this. So whenever we are inserting a new element, we know at which point we need to insert that element. I mean, we know, okay, that if the next element would be added, the tree would look something like this, right? Because it's a balanced tree. So you insert an element here. When you insert an element here, the property that I mentioned could be violated. So it could be that if I'm inserting an element here, if this follows the relation B less than D, then we are fine. However, if it does not follow this relation, that is, if B is greater than D, if B is greater than D, then what we can do is we can swap D and B. If we do that, let's say this element was E, we know that B is less than E, and we have this relation that B is greater than D, that is, D is less than B. So if we swap that, then D comes here, B comes here, and we know that using these two relations, D would be less than E, because D is less than B and B is less than E. So that means D is less than E. So the relation is followed in this subtree. Now this operation that we did of percolating D up is called percolate up, right? So now we do the same thing for comparing D with A. If D is greater than A, we are fine. Meaning if D is greater than A, then we are fine. The property is followed. If it's not, we again do the swap thing. Okay? We keep on doing this as long as the property is violated. So we'll end up at a position where the property is not violated and D finds its right position. So this is how we do an insert. A similar thing could be done for delete. So I'm not going to cover that. Anyhow, in C++, if you want to use something like heap, there's a data, we'll be covering STL later today. There's a structure by name of priority underscore queue, or there's a heap as well. You can use that. You don't need to go into the implementation details, but we're just telling you because these techniques come in handy when you're actually solving a problem.
So I'll now move to another data structure which is like kind of very used data structure, very useful. It's called a trie or a keyword tree. So trie is typically used for all string operations. Mostly many of the string problems can be solved using a trie. So we'll discuss a trie. Trie is very much similar to a dictionary. So if you have to construct a dictionary, trie is the right data structure to use. So the structure of trie is So there is a root node, and this root node has 26 children if we are considering the English alphabet. Typically, I mean, you can customize a try as per your convenience, as per your language. It may have 26 letters, it may have only vowels. It depends on the problem requirement. But I'll be discussing this particular for English language. So this will have 26 children. Each of the node of the try will have 26 children, and it's a tree like a structure. So there is a root, there are 26 nodes for A, B, C and Z respectively, and similarly each of these nodes will again have the same structure. Each of these nodes will have 26 children, each representing A, B, C, D until Z. So typically in a try what we do is that suppose there is a string, maybe like the string is Nitin, say there is a name Nitin. So what we do is that we take the root, we follow the links of these these letters. So this particular root will have 26 nodes as its children, in which one of them will be N. So we'll follow this link and we will go to N. And this N will have I, so we'll follow this link again and we'll go to I. Then to T, then again I, and then again N. So this is the way we'll insert Nitin in this particular try. Now suppose there is another name, another word, say another name, say Nilesh comes up, and you want to insert it again in this try itself. So you can see that the N node is already created. So you'll follow this link N, and then I, and then you need L. Now there is no L here because there was no word inserted in this try which has a prefix with NIL. So you will create this node L for L and you will follow this. Again, when similar thing which you followed for the Nitin thing, you will go and follow E and then S and then H. So whatever prefix is common, that's taken only once in a try. So problems like suppose you want to build a directory of numbers, so you can always do it for numbers. You will have 10 nodes from 0 to 9 for each, and whenever you need to search a number, you will just have to follow the links at each node. Like if you are searching for 934, you will go from 9 to 3 to 4, and if at some point that particular node doesn't exist, that means that that number doesn't exist. So another thing is that typically English, like there are like two strings, there can be two strings in a data set in which the first string can be the prefix of the second string. So at presently, if we see, we'll find a name always at the end position. But suppose there is one name which is one word which is like NIT, and it may be a valid word. So with every node we need to associate an information whether this is end of a word or not. So we have is end boolean variable which will tell us whether this is a valid word or not till that point. Yeah.
NIL is there.
Yeah.
After that, after L, I comes.
Yeah.
Then how will you map it out?
Okay. Yeah. NIL. Yeah.
I comes.
When I comes, so it will come in the branch of L. So you'll follow NIL and go to this branch of I.
Can't we use the existing?
No, you can't use the existing because this particular NI is signifying the prefix NI. And now you are trying to signify the same